So, we have discussed fitting of data using two methods, two numerical methods. One is called as the Lagrange's polynomial method, and the other one is the Newton's polynomial method. And now we are going to learn the regression method, which is purely based on the statistics that we have learned in the previous lecture. So, we are talking about linear regression, and let us understand that what it means. Okay. So, we know that the equation of a straight line is nothing but y equal to a naught plus a 1 x plus some e. We do not write it with a e usually, we write it simply a 0 plus a 1 x, where a 0 is the intercept on the y axis and a 1 is the slope. But then this e is included as an error or the discrepancy to the true data. So, you have a table of data which xi and yi are given, where I runs from 1 to n are the number of data points, and you want to fit it to a straight line. And let us see how do we do that. And this e actually corresponds to the error or the deviation from each one of those data points given by xi and yi. So, needless to say that your a 0 is the intercept, a 1 is slope, and e is the error of these line from the data points. So, the error which is important here shows the discrepancy between the true data which is value of y, say for example, that is value of y, and the approximate value given by the straight line, which is equal to a 0 plus a 1 x, which is predicted by the linear line or the linear in this case the straight line. Okay. So, we want to have a best fit of this. Best fit of data for a given linear relationship as it is given here. So, if you want to get a best fit, one has to follow certain procedures. Let us see what the procedure is. So, one strategy, we will call it 1. So, this is for fitting a straight line through the data would be to minimize the error. Error, or basically we are talking about the sum of the error, or which is called as sum of the residual errors. I will tell you what it means. Let us highlight this, and corresponding to all data points. Okay. So, what I mean is that we have to minimize a quantity called as E I, sum over I runs from say 1 to n, n is the total number of data points, and which from the linear equation we can write it as y I minus a 0 minus a 1 x I, and so n is the total number of so what we need to do is that we need to minimize this error, so that the data that we have obtained either from a numerical simulation or from an experiment, that can be fitted to a straight line. And if you try to do that, you find that this is an insufficient condition. And why it is an insufficient condition? Let us take an example of there are say 3 data points, and one can actually draw a straight line through this data point, all these 3 data points. But you see, if you want to minimize this, even this line, let me draw it with a different color, even this line which passes through the midpoint of these 3 lines is an equally probable plot, though it looks really bad, but this also, this red line and the bold. So, let us write the red line, let us write it as a continuous line. So, this red line and the, so both red and black both would minimize EI. Okay. So, clearly the red line is not a fit to the curve, but it satisfies this criterion, which means that this criterion or this condition is insufficient. And if we could look at a slightly better one, then we would write it as this is number 2, and in so a more logical one, at least seems like, is a minimization of the absolute values of the discrepancies. So, this is like EI, and we have a I equal to 1 to n. We have taken the magnitude, ignored the sign of this, and this is equal to I equal to 1 to n, and a y I minus a 0 minus a 1 x I. So, you need to minimize this, but this is also not sufficient, because let us draw again these 3 points, say for example, so this and draw a straight line through these points, and another line which is like this. Let us draw it with a different color as we have done for the earlier one. So, any line between the black line and the red line, that would also minimize this error or the absolute value of the error. So, any line between the black line and the red line would minimize this quantity. Okay. So, clearly the red line is not a good fit to the data that is given there. So, a more accurate and possibly the only method that would do the job that we are looking for. So, third one is that minimize the sum of the squares. So, importantly we have tried to minimize the error, then the magnitude of the error, and now we are trying to minimize the the sum of the squares of this error, which means that we are going to minimize this SR, and SR is nothing but I equal to 1 to n and the EI square, which is nothing but I equal to 1 to n and YI measured, say for example, and y I by this model of linear regression. So, this is nothing but we need to actually talk about this 1 to n, and we have a y I minus a 0 minus a 1 x I square. Okay. So, this SR needs to be minimized, and if you minimize, it turns out that if you minimize SR, then you would the job would be done, that is, that would provide the best fit, a linear fit of the data that we are trying to fit. Okay. It is important to note one thing here. SR is actually a function of two parameters, A0 and A1. Most of the times in physics and in other engineering disciplines or even in other science disciplines, one comes across a function which is only a function of a single variable, and when it is a function of single variable and we need to find the position or rather the value of x for which it is minimum. Okay. It could be minimum or maximum, which finally would have to be cross checked with the double derivative whether it has a positive sign or a negative sign, because for a positive sign one actually talks about a minima, and for negative sign one talks about a maxima, because the double derivative actually measures the curvature of a function at that point. So, if the curvature is positive, that means we are at the minimum position, and if the curvature is negative, then we are at the maximum position. In any case, most of the time we disregard that subtlety, and we try, when we try to look for a minimum condition, we take a derivative of that function and put that function to 0 and find out at what value of x that function has a minimum value. Here importantly, we have two variables which needs to be minimized in order to see the minimum of these SR. So, we have a parameter space which is bigger than one variable. It is a two variable parameter space, but that really is not a problem, because we want to we can do a derivative, we can take a partial derivative with respect to each one of those A0 and A1 and individually put them equal to 0, so that we know that the DSR is equal to 0. So, but before that, so let me claim almost a priori that this yields, this third strategy yields a unique line for a given set of data points. So, let us look at the least square fit of a straight line. So, we have to determine A0 and A1. So, the way we do that is that we take partial derivatives of this SR with respect to A0, which simply gives a minus 2 sum over I equal to 1 to n and a y I minus a A0 minus a A1, sorry, this is not I, this is A1, which is the slope, and x I and so on. And if you do it, take a partial derivative with respect to A1, then it is a minus 2 and there is a x I and it's a y I minus A0 minus A1 x I. Okay. So, we can set these setting these derivatives equal to 0 gives minimum SR. Okay. And if that is a strategy, then of course, it is easy to do. So, we will put this derivatives equal to 0. So, 0 equal to my I mean this 2 has no meaning then. So, you have a I and a y I minus a sum over I A 0 minus A 1 sum over I x I. Okay. And then again I will put the left the second one equal to 0. So, this is equal to a sum over x I y I and a sum over I and minus A 0 sum over x I and minus A 1 x I square and so on. Now, identify that this quantity that is sum over A 0 sum over I is nothing but n A 0, where n is the total number of data points. So, then I can write down this slightly reorganize the equation and can write it as n A 0 plus sum over I x I A 1. So, this is I A 1 equal to sum over y I. Okay. And there is a sum over I x I with a 0 plus a sum over x I square and a 1. So, if I miss these i's, please understand that these mean that it is a sum over I going from 1 to n, and this is equal to nothing but a x I y I. Okay. So, these are the two equations that we need to solve for the A 0 and A 1, which are the important ingredients to the line that we are trying to fit our data. So, these two things, if you solve these two equations for the two variables A 0 and A 1, one gets A 1 equal to n sum over I x I y I and minus sum over I x I sum over I y I divided by n x I square and x I square this square. So, please make sure that you do not get confused. So, this is a sum over I x I y I. So, that is a product of each of the data points and then you sum over, and this is you sum over all the data points and the, I mean basically the corresponding values and then take a product. So, these two are not same, and in the similar way we are taking the product or rather the square of these sum of the squares, and this is a square of the sum. Okay. So, these are not same, and the a0 is actually nothing but a y minus a1 x, where y bar and x bar are mean values of y and x. All right. Okay. So, this page or rather this slide summarizes everything, that we have taken the square of these error and have minimized it with respect to the two unknown parameters, which are a0 and a1, and put them equal to 0, and there from there we have solved for a0 and a1, which comes in terms of the data points like this. All right. So, take a table. So, let us take an example. It is a book example, but you can take any example for that matter. Take an example that you have performed in your lab, maybe the steam table for in your thermodynamics course, or maybe a physics course, a simple pendulum experiment, or for that matter in a chemistry lab when you do all these experiments of say measuring something with respect to time and so on. So, you can take any of these data. We are just taking an illustrative table. So, xi, yi, and because I would need it, so I am computing this, and then also I am computing the error. Okay. So, we have 1, 2, 3, 4, 5, 6, 7, and you have these corresponding values for the yi are 0.5, 2.5, 2.0, 4.0, 3.5, 6.0, 5.5, and so on. So, these are corresponding data points, and I can easily calculate this yi. So, there is a sum over yi which comes out as 24.0. If you can add all these numbers, it will come out as that, and we can also get this y bar, which is 24.0 divided by, because there are 7 data points. So, we divide it by 7. So, these numbers, so this is like a 3.42686. We will keep only 4 decimal places. So, 4286. Okay. So, you can check that. Now, each one of them I will subtract from each one of these yi values. I will subtract this 3.4286 and take a absolute value of that, which is the mod that is shown here. So, this is like a 8.5765. So, this is yi, and minus of this, so this has to be done. So, maybe this data we have written is, so it is a 0.5 and minus 3.42, but then you have to take this thing there. So, it should be so 0.5 and minus this would be so 0.5 minus 3.4286 would give me, so this is like a 0.5 here, 0.500. So, this is like a 6 and 8 and 2, and so this is like a 9, and this is like a 2. This is a 2 and so on, and then of course, it is negative, but we will take the this value. So, it is 0.9286. please see these things 2.9286. Then we have this as 0.8622, and this is like 2.0408, 0.3265 and 0.0051, and well, I 0.0051, 0.0051 and 6.6122, 4.2908 and so on. So, please see these data, and should be fine. Even if I made some mistakes, you should not repeat that, you should do it yourself. So, this is yi minus y bar, and if you calculate these data, so it is 0.1687, 0.5625, 0.3473, 0.3265, 0.5896 and 0.7972 and 0.1993. And if you take the sum of these, then it becomes equal to 2.9911. Okay. So, the reason that we did is following, we will show that. So, here let us analyze what we have done and how we can calculate a best fit line of this. So, number of data points equal to 7, which is your value of n. Sum over x I y I equal to 119.5, and sum over I x I square equal to 140, and sum over x I equal to 28. These are the values that are added from 1 to 7. So, is these values that are added. Okay. We need all these x I, y I and x I square and x I sum over all that. Also we need, because A0 demands the knowledge of mean x. So, which is equal to 28 over 7, which is equal to 4, or we can write it as 4.0. Y bar is nothing but sum over y I over n, which is equal to 24 over 7, which is already been calculated, 428586 and so on. So, these are our preliminary calculations of all these average values of x I, y I, x I y I and x I square and things like that. So, if you plug in into the formula for A1, which is the slope, which is here in this formula, if we plug in these things, this formula that we plug in and this formula that we plug in, then of course, your A1 becomes equal to n sum over I x I y I and sum over x I. I have written that once again for your reference, n x I square minus I x I square. Okay. So, if you put in all the values that we have obtained, 119.5, because n is equal to 7, and x I y I has a value 119.5. So, this is equal to 28 multiplied by 24, and this is like 7 into 140 and minus 28 square, which is the x I and all that. So, this taking the square of that, and if you simplify this, this comes out as 0.8393, and A0 is simply equal to 3.42. So, A 0 is if you want me to write down, it is y bar minus A 1 x bar, y bar minus A 1 x bar. So, this is equal to 3.4286 minus 8393 multiplied by 4, which is equal to 0.0714. Please see these calculations. So, thus the least square fit y equal to 0.0714 plus a 0.8393, sorry. Okay. So, this is equal to your A 0 and this is equal to your slope A 1, and this is the best fit line for that particular table of data that we have seen. But how do we know that? How do we know that this is the best fit line? This is the intercept and this is the slope that will fit the data that is that are given that fits it the I mean this line fits those data the best. So, of course, I mean goes without saying that any other line, any line other than this results in a larger sum of the squares of the residual. So, the calculated this line is the best fit through all the data points So, this is the best fit line through all the data points. How do we say that? We will see it in a while, but let me make these comments a priori. One is that, so these are comments. One is that the spread of the data points given by y I minus a 0 minus a 1 x I square around the line is of similar magnitude. Let me see what I mean by that. What I mean is the following, that if you look at this last column, let us this laser pointer, if you look at this last column, you see that all are between 0 and 1, and rather it is centered around some values which are like 0.3 and so there are some values like 0.79 to some 1.16 and all that, but there is no number which is like of the order of 1 and the other is of the order of 10. So, they are of the same order, and this is a feature that we have been able to minimize the residual error, some of the residual error. Okay. So, they are similar in magnitude. And the second thing is that, which I will not elaborate here, but will do another example in which we will show this. Also the distribution of points is normal. So, it corresponds to a normal distribution, which is what we have discussed earlier. So, this is a check that you should do, but we will give you another check. If you look at two plots, so you have a line and you have data points like this, and so on. So, this is called let us call this as A, this is called as a linear regression with small errors and take another one. These are freehand drawings. So, I just wanted to make the point clear. So, this is like and so on. So, this is B, this is again the linear regression with relatively large errors. I mean larger than the plot in A. Let us see a physical problem where you can apply it. Okay. So, a velocity of a falling object in a viscous fluid. Okay. This could be just a parachutist falling down, or maybe a ball falling down through paraffin or honey. So, it could be anything. So, we write down the Newton's equation of motion as m dv dt is equal to F, and the F is the force that acts. This is equal to due to gravity. So, we will write it with a G, and a resistance force, because I have said it is a viscous fluid. So, we will write it with a R. So, G corresponds to gravitation and R corresponds to resistance. So, F g equal to m g, F r equal to minus alpha v. So, this is an assumption. This is the most simple assumption that the resistive force that the body experiences while traversing through the viscous fluid, it is proportional to the velocity. It could be velocity square or even larger power of the velocity. But for small viscosity, that is when we talk about normal fluids, we usually take it as a single power of v. So, this v is the velocity, and so we can write down as dv dt, this is equal to a g minus alpha by m into v, and so v of t can be g m over alpha and 1 minus exponential minus alpha by m t. Okay. We certainly do not have a linear equation. We have an equation which is has a very nonlinear dependence, v as a function of t. So, if you want to measure the velocity of the particle at discrete time steps and make a table out of it and want to fit it with a linear regression, you could see what happens. I am not doing this problem, but posing a question to you, that is linear regression at all a good approximation for this, the data that you would be generating from this equation, or it is completely it does not make sense at all to have a linear fit of this, or it makes sense in some part of the plot that it generates, it only makes sense in that part of the plot and does not make sense in other parts of the plot. Please think over this and so on. So, but you can calculate this or rather put some discrete time steps, let t equal to 1 second, 3 seconds, 5 seconds, 7 seconds and all that, and calculate v by putting knowing all these values of g. G is of course the acceleration due to gravity, which is 9.8 meter per second square, and alpha is the coefficient of the viscosity of the viscous coefficient, which would for a particular fluid it will have a value, and mass m is the mass of the particle, which is of course would be given to you. So, for given g m alpha, one can make a table. Okay. So, of course, it looks like to you that maybe when these alpha over m to be a very small quantity, then a linear approximation would hold. That is, if the mass is small and the alpha is very large, then of course, or rather it is let us not talk about the values per se, but let us say that we can make a linear approximation out of these things, then we can have this. Of course, if alpha is very large, the motion would stop almost immediately, but if you expand this exponential and keep only the linear term, then you will have a linear equation. So, the question that I am posing to you is that in what regime these linear fit would hold, and after that your linear fit would no longer be a good approximation to fit the data, or a good model to fit your data. So, this makes us go to the next level of fitting, that is, we can do a, instead of a linear regression, we can do a polynomial regression, that is, invoke larger power of x. And as we will see that the problem is not too difficult, it is in fact a trivial problem of getting or rather raising the difficulty to a polynomial regression. So, this is a polynomial regression. So, now and polynomial is, as you know, that is equal to, it involves all powers of x, that is a0 plus a1 x plus a2 x square plus a3 x cube plus a4 x to the power 5 and so on. So, this is like y equal to something like n a n x n. So, n will vary from 0 to some power that you are interested in, but let us just talk about a quadratic equation. Okay. So, we have y equal to a0 plus a1 x plus a2 x square and plus e, that is the sum of the residuals, and we are going to take the same route as we have taken earlier, that is, we are going to minimize the sum of the residuals, that is we are going to minimize this quantity. Now, we have a quadratic term that is extra, and that of course raises the problem to one order more, or rather it increases the size of the problem to an order more. So, it is x I and minus a2 x I square, and this has to be minimized with respect to. So, this is the square of this has to be minimized with respect to now 3 parameters, namely the a0, a1 and a2. Okay. So, we have 3 equations. So, again following the same procedure of minimizing them, it is this sum over I and a y I is a0 a1 x I minus a2 x I square del SR del a1 it's equal to minus 2 sum over I x I y I minus a 0 minus a 1 x I minus a 2 x I square del S R del a 2 it's equal to minus this x I square y I minus a 0 a 1 x I minus a 2 x I square. So, this is the three equations that you have to solve, and if you set your sum over a 0 equal to n a 0. So, we get three equations which are like n a 0 plus sum over I x I a 1 plus sum over I x I square a 2, this is equal to sum over I y I, and this is sum over I x I a 0. So, this sum over I means the sum goes from 1 to n plus x I square a 1 and plus x I cube a 2, this is equal to nothing but x I y I, and we have x I square a 0 plus x I cube a 1 plus x I 4 a 2, it's equal to x I square y I. Okay. So, these are these are simple, you can easily figure out these equations x I square y I and so on. So, these are again three equations and with three unknowns, and usually we do not try to solve it by this elimination method, or rather this substitution method. What we can do is that we can write down sort of code for Gauss elimination, which we will see later, and then calculate these a 0, a 1 and a 2, and let's take a quick example of that here. So, we will convert this equation into a matrix equation and solve it using Gauss elimination method, and as I said earlier that we will see this usage and applicability of this method later. So, an example. So, we have a x I, we have a y I, we have a y I minus y square, and we have a y I minus a 0 a 1 x I minus a 2 x I square and the whole square of that. So, then maybe we have just 5 data points. So, 1, 2, 3, 4, 5, and here we write down the results of that. So, this is a 0, 1, 2, okay, we have 6 data points, 3, 4, 5, and we need little more space here in order to calculate these sums and all that. So, y I is like 2.1, 7.7, some experiments have given this, 13.6, 27.2, 40.9, 61.1. Okay. So, if you sum this comes out as 152.6. So, this is like 544.44, 314.47 and 140.03, this is 3.12, 239.22, and 1272.11, and so this sum of this is equal to 2513.39. Now, this is 0.433, 1.0029 and 1.0816 and 0.8049, and these are 0.6195, there is 0.0944, and if you take the sum of that, this becomes 3.7466. So, using these three equations that we have written down in the previous slide, let us try to solve this. So, these are these xi's and all that. So, it is 6, 15, 55, 15, 55, 225, 55, 225, 979, and this is A0, A1 and A2, and this is equal to 152.6, 585.6, 2488.8. So, these are these things which are yi, xi yi and xi square yi. So, those had to be calculated and so on. So, this is these are the three equations that one need to solve, and at this moment I am not getting into the details of the solution, but it can be done by a variety of methods, and one of them being Gauss elimination. So, one can get a A0 equal to 2.4786, A1 equal to 2.3593 and A2 equal to 1.8607. So, what we get is that we get a quadratic fit, that is a quadratic line which fits the data is 2.47857 plus a 2.35, that is the slope 93, so 86, let us call it simply 86, 93x and plus 1.8607 x square. So, this is the best fit to the line. Now, why is this the best fit to the line? Let us see that. So, we can calculate the standard deviation of this data, and the standard deviation, I am not going into details of that, but the standard deviation for this particular case can be calculated as, so it is SS is equal to SR, that is the residual error SR that we have defined, and it is n minus 3. Now, this 3 comes in the denominator because of A0, A1 and A2, these are 3 in number. So, we actually lost 3 degrees of freedom, and that is why this is n minus 3, and this S actually can be x or y depending on which variable is a the dependent variable and the independent variable. It is rather the dependent variable. So, in this particular case S is equal to y. So, here if we calculate this SR, which we have already calculated here, that is this one 3.7466, which is the sum of the residual squares. So, if I put it here 3.7466 and then n is equal to 6, because it goes from 0 to 5 and it is this, and then if you do this calculation, then it comes out as 1.12. So, that is a standard deviation, but that does not say much, it only says that the standard deviation is quite small. But however, what is more important in this particular context is calculating a quantity called as R, or which the quantity that measures the goodness of data, that is how goodness of fit, rather not data, or the data versus the fit is computed by a quantity called as a R square, which is that S y, we are writing it explicitly, it is actually SS, the one that is introduced in the last slide. So, S is equal to y here minus SR divided by SY. So, SY is nothing but the total sum of the squares around the mean of the dependent variable. So, this turns out that it is like 2513, we have calculated this already, 0.39 minus 3.74657 divided by 2513.39. So, this is equal to 0.99851, which means that this means that 99.851% of the original uncertainty has been explained by this quadratic fit. Okay. And which means that it is a very good approximation, this quadratic approximation, or this quadratic regression that we have done is a very good approximation to the data that is shown there. In fact, what you could do is that you could do a linear regression for this. Just remember one point here, the linear regression would have a n minus 2, because this 2 is the number of these parameters that we actually find out, and then you use the same formula as here, and you can see that the quadratic fit is a much better approximation, or the quadratic regression is a much better approximation for the data in this particular case. In the similar fashion, the polynomial regression can be built up. Every time you increase a power, that is, if you want to do a cubic fit of this data, your order of equations go up by 1, that is the number of equations that you need to solve go up by 1. And in principle, it is not a problem numerically, but then writing it over and over again for a large matrix would be problem, but then you need to do that if you really want to fit very sort of scattered data with a polynomial having a large degree. So, I believe that I have been able to explain that why these linear regressions and quadratic regressions are done for a set of data that you have found either by experiments or by numerical simulations, and you need to know the analytic behavior of the data. Suppose the data is actually diverging. Now, of course, in your linear fit or a quadratic fit, it is hard to catch, but then you can do these kind of fits in presence, or rather in the vicinity of the points where it is showing an anomalous behavior, and you want to know what is the nature of the anomalous behavior. If it is a diverging quantity, then how is it diverging? What kind of singularity exists? Is it a removable or a non-removable singularity? And all these questions are important both in physics and science, in other branches of science and in engineering, that we need to understand the behavior of a function from a collection of data. That's is the that is the motive behind doing all these exercise.